20 garages each with its own service drop create 20 separate electrical subpanels. A common water line runs through all 20 garages, acting as a continuous conductor. There is no bonding jumper or grounding electrode connecting the water line to the electrical system in garage 10. This situation creates a very dangerous scenario. The water line is acting as a ground conductor, but without proper bonding, it poses a significant electrical shock hazard. Firstly, the absence of a grounding electrode system at garage 10 means there is no low impedance path for fault current to return to the source. Secondly, if a fault occurs in any of the garages connected to this water line, the fault current will travel through the water line. Thirdly, the absence of proper bonding at garage 10 creates a high resistance path, which can cause the water line to become energized. This energized water line presents a severe risk of electric shock to anyone who comes into contact with it, especially if they are also in contact with another grounded surface. Electrical codes, like the National Electrical Code, NEC, have very specific requirements for grounding and bonding to prevent such hazards. These requirements are in place to ensure electrical safety and minimize the risk of electric shock. The NEC, for example, Article 250 covers grounding and bonding requirements. Grounding creates a low impedance path for fault current, allowing overcurrent protective devices, such as circuit breakers or fuses, to quickly clear the fault. Bonding ensures that all metallic parts that are likely to become energized are connected together, creating an equipotential plane. This reduces the voltage difference between different metallic surfaces, minimizing the risk of shock. In the scenario described, the water line should be properly bonded to the electrical system in each garage, including garage 10. This bonding should be done using a bonding jumper of appropriate size, as specified by the NEC Table 250.102. The bonding jumper should connect the water line to the grounding electrode conductor or the grounding busbar in the electrical panel. In addition to bonding the water line, a grounding electrode system should be installed at each service. This grounding electrode system can consist of various components such as a ground rod, a ground plate, or a concrete encased electrode U for ground. The grounding electrode system provides a direct connection to the earth, further reducing the risk of electric shock. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified by NEC Table 250.66. It's essential to ensure that all grounding and bonding connections are made properly and are secure. Loose or corroded connections can increase resistance and reduce the effectiveness of the grounding system. Regular inspections and maintenance of the electrical system are also crucial to identify and address any potential issues. Qualified electricians should perform all electrical work to ensure compliance with electrical codes and safety standards. Improper electrical work can have serious consequences, including electric shock, fire, and property damage. Here are some specific recommendations for addressing the situation in the 20 garages. Firstly, immediately disconnect the power to all 20 garages until a qualified electrician can inspect the electrical systems. Secondly, hire a licensed electrician to evaluate the grounding and bonding of each garage's electrical system. Thirdly, ensure that each garage has a properly installed grounding electrode system, such as ground rods or a connection to a concrete encased electrode. Fourthly, bond the water line to the electrical system in each garage, using appropriately sized bonding jumpers according to NEC Table 250.102. Fifthly, verify that all electrical connections are tight and free of corrosion. Sixthly, conduct a thorough inspection of the electrical panels and wiring in each garage to identify any other potential hazards. Seventhly, correct any identified deficiencies to bring the electrical systems into compliance with the NEC and local electrical codes. Eighthly, provide electrical safety training to all occupants of the garages to raise awareness of potential hazards and safe practices. Ninthly, install ground fault circuit interrupter, GFCI, protection for all receptacles in the garages, especially those located near water sources. Tenthly, consider installing a whole building surge protective device, SPD, to protect sensitive electronic equipment from voltage surges. In summary, the daisy chain of unbonded electrical subpanels connected by a common water line is a dangerous situation that requires immediate attention. Proper grounding and bonding are essential for electrical safety, and compliance with electrical codes is crucial to prevent electric shock hazards. It is imperative to engage a qualified electrician to evaluate and correct the electrical systems in these garages to ensure the safety of all occupants. Ignoring these issues can lead to serious injuries or even fatalities. Now, let's delve deeper into the technical aspects of grounding and bonding, explaining why these practices are so critical for electrical safety. Grounding, in its simplest form, is the intentional connection of a conductive object to the earth. This connection provides a low impedance path for fault current to flow back to the source, typically the electrical panel. The earth itself is a relatively poor conductor of electricity, but it serves as a reference point for voltage potential. By grounding electrical systems, we establish a common reference point and minimize the risk of voltage differences between different conductive surfaces. When a fault occurs, such as a short circuit between a live wire and a metal enclosure, the fault current will flow through the grounding path back to the source. This high current flow will trip the circuit breaker or blow the fuse, quickly interrupting the power supply and preventing a prolonged electrical hazard. Without a proper grounding path, the fault current may find other paths to ground, such as through a person's body, resulting in electric shock. Bonding, on the other hand, is the process of connecting together all metal parts that are likely to become energized. This includes metal conduits, metal enclosures, metal water pipes, and other metallic objects. The purpose of bonding is to create an equipotential plane, meaning that all bonded metal parts are the same voltage potential. This minimizes the voltage difference between different metallic surfaces, reducing the risk of electric shock. When a fault occurs, the fault current will flow through the bonding conductors, ensuring that all bonded metal parts rise in voltage potential together. This prevents a voltage difference from developing between different metal surfaces, which could cause a shock if a person touches two different surfaces simultaneously. The size of the bonding conductors is determined by the size of the circuit conductors, as specified by the NEC Table 250.102. It's important to use the correct size of bonding conductors to ensure that they can safely carry the fault current. Now, let's consider the specific requirements for grounding and bonding in a multi-building installation such as the 20 garages described in the original scenario. According to the NEC, each building or structure that is supplied by a feeder or branch circuit must have its own grounding electrode system unless certain conditions are met. These conditions typically involve having a qualified person ensure that there is an effective ground fault current path back to the source. In the case of the 20 garages, each garage would likely require its own grounding electrode system. This grounding electrode system could consist of ground rods, ground plates, or a concrete encased electrode. The grounding electrode system should be connected to the grounding busbar in the electrical panel using a grounding electrode conductor. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified by NEC Table 250.66. In addition to the grounding electrode system, a metal water pipe must also be bonded to the electrical system. This bonding should be done using a bonding jumper of appropriate size, as specified by NEC Table 250.102. The bonding jumper should connect the water pipe to the grounding electrode conductor or the grounding busbar in the electrical panel. It's important to note that the water pipe can only be used as a grounding electrode if it meets certain requirements, such as being in direct contact with the earth for at least 10 feet. If the water pipe does not meet these requirements, it cannot be used as the sole grounding electrode. In this case, an additional grounding electrode, such as a ground rod, would be required. Furthermore, it's important to ensure that all metal parts that are likely to become energized are bonded together. This includes metal conduit, metal enclosures, and other metallic objects. The bonding conductors should be sized according to NEC Table 250.102 and should be securely connected to the metal parts. In the case of the 20 garages, it's also important to consider the potential for stray currents. Stray currents are unwanted electrical currents that can flow through the earth or through metal structures. These currents can be caused by a variety of factors, such as unbalanced loads, faulty wiring, or improper grounding. Stray currents can cause corrosion of metal pipes and equipment, and they can also create electrical hazards. To minimize the risk of stray currents, it's important to ensure that all electrical systems are properly grounded and bonded. It's also important to use ground fault circuit interrupters (GFCIs) to protect against ground faults. GFCIs are devices that detect small amounts of current leakage to ground and quickly interrupt the power supply. They are particularly effective at preventing electric shock. Now let's discuss the importance of regular inspections and maintenance of electrical systems. The electrical system should be inspected regularly by qualified electricians to identify any potential hazards or deficiencies. Inspections should include checking the grounding and bonding connections, testing the GFCIs, and inspecting the wiring for damage or deterioration. Any identified deficiencies should be corrected promptly to ensure the safety of the electrical system. Maintenance should also be performed regularly to keep the electrical system in good working order. This includes cleaning electrical panels, tightening connections, and replacing worn or damaged components. Proper maintenance can help to prevent electrical failures and extend the life of the electrical system. In addition to regular inspections and maintenance, it's also important to provide electrical safety training to all occupants of the building. This training should cover topics such as recognizing electrical hazards, using electrical equipment safely, and responding to electrical emergencies. By educating occupants about electrical safety, we can help to prevent accidents and injuries. Now let's summarize the key points of this discussion. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source. Bonding creates an equipotential plane, minimizing the voltage difference between different metallic surfaces. Multi-building installations require special attention to grounding and bonding. Each building should have its own grounding electrode system. Metal water pipes must be bonded to the electrical system. All metal pipes that are likely to become energized must be bonded together. Regular inspections and maintenance are crucial for electrical safety. Electrical safety training should be provided to all occupants. By following these guidelines, we can help to ensure the safety of electrical systems and prevent electric shock hazards. Remember, electrical work should always be performed by qualified electricians who are familiar with electrical codes and safety standards. Improper electrical work can have serious consequences, including electric shock, fire, and property damage. Always err on the side of caution and seek professional assistance when dealing with electrical systems. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician before performing any electrical work. Safety is paramount when dealing with electricity. Take the necessary precautions to protect yourself and others from electrical hazards. Now, to further emphasize the importance of proper grounding and bonding, let's consider some real-world examples of what can happen when these practices are not followed correctly. Firstly, consider a scenario where a metal water pipe is not properly bonded to the electrical system. If a fault occurs, such as a live wire coming into contact with the water pipe can become energized. If someone then touches the energized water pipe while also in contact with another grounded surface, such as a concrete floor, they can receive a severe electric shock. Secondly, consider a scenario where a grounding electrode system is not properly installed. If a lightning strike occurs, the lightning current may not have a proper path to ground. This can cause the lightning current to flow through other paths, such as through the building's wiring or through the earth. This can damage electrical equipment, start a fire, or even cause an explosion. Thirdly, consider a scenario where a ground fault circuit interrupter (GFCI) is not installed in a wet location, such as a bathroom or kitchen. If an electrical appliance comes into contact with water, a ground fault can occur. If someone then touches the faulty appliance while also in contact with a grounded surface, they can receive a severe electric shock. These examples illustrate the importance of following electrical codes and safety standards. Proper grounding and bonding, along with the use of GFCIs, can significantly reduce the risk of electric shock and other electrical hazards. Remember, electricity is a powerful force that must be treated with respect. Always take the necessary precautions to protect yourself and others from electrical hazards. When in doubt, consult with a qualified electrician.